Let me start our recording. Okay, so in the last class, we discussed about subthreshold swing. The subthreshold swing, the unit of subthreshold swing is millivolt per decade. This is nothing but inverse of subthreshold slope, right? And when I'm talking about subthreshold slope, so if you look at the IV characteristics, so here I have plotted a log y-axis and x-axis linear. So this is my threshold voltage. So this point is your threshold voltage, and this is the subthreshold part, right? So below threshold, VGS below threshold, and this is above threshold. Uh, in the subthreshold region, your current is exponentially related to VGS that we have derived in the last week, right? Your current is exponentially related to VGS, and in the above threshold voltage, your current is quadratically related to VGS, right? So subthreshold slope. This is nothing but the slope of this line here, right? So, right, and swing is the inverse of that subthreshold slope. And we have derived this equation for subthreshold swing, which is 2.3 m kt by q. And so here you see the slope or the swing, right? Whatever you tell it, right? Subthreshold slope or subthreshold swing, they are equivalent, but subthreshold swing is 1 by subthreshold slope, right? So this depends on temperature, right? And M factor, right? M factor is our gate control, right? So I had told you earlier. So your M factor, which is nothing but 1 plus CD by Cox. So this just tells you how your psi, the change with gate voltage, right? So this is your gate control, right? So this is the gate control, right? If your gate control is very good, your subthreshold swing will be better. Means lower, right? Your slope will be higher. Okay. So ideally, when you are designing your transistor, you want your M to be very close to 1 or equal to 1. If I do M equal to 1 here, then subthreshold swing will be 60 millivolt per decade, right? 60 millivolt per decade. This is the ideal subthreshold swing. We cannot go below that in the conventional MOS transistor, right? Okay. So this subthreshold swing decides your off current, right? Because if you know your threshold voltage, right, your current at the threshold. So let's say this is current when VGS equal to this is your I threshold. So if you know the subthreshold swing, you know I threshold, you could find the off current, right? If your subthreshold swing is higher, let's say this is 60 millivolt per decade is ideal. If it is 80 millivolt decade, your off current will be higher, right? So basically, you do not want your off current to be very high. That's the reason you want to keep your subthreshold swing very close to 60 millivolt per decade. So also we talked about on current. On current is, this is the ideal on current. So without any second order effects, which we'll discuss. So without any second order effects, your on current is mu Cx double by 2L VDD minus VTS square, right? So here you see there is, so your on current will depend on threshold voltage. Lower the threshold voltage, your on current will be higher. But lower the threshold voltage, that means your VTS is shifting. If a threshold voltage is low, that means your VTS is shifting this side, your off current will be higher. Why? Because if you see, if a threshold voltage is decreased, that means this off current will increase, right? Right. So there is a trade-off between on current and off current, and so that trade-off is typically shown in a curve called universal curve. So universal curve is a typical curve which is used to qualify your technology, right? So and sell your technology also, right? So this just plots on current in the x-axis and off current in the y-axis for transistors with different length, right? So when you talk about your universal curve, you need multiple points. I told you, right? On current is a specific current for a particular transistor, right? If you want to plot universal curve for a single transistor, then it will be 1 point, right? 1 point, right? Right? Because every transistor has a particular I on and particular I off, right? But this curve is generated by plotting for different gate length, right? Different length transistors, right? So let's say this is my 180 nanometer technology. So my nominal gate length is 180 nanometer. So I could plot for different, like I can plot for 130 nanometer technology, not technology, same technology for different gate length, right? Or let me not confuse you. So let me put it like this, right? So if this is my nominal length, right? L nominal length is the minimum gate length which everybody uses, right? So this is the nominal gate length of a particular technology, right? So I go nominal minus delta, L nominal minus 2 delta, or L nominal plus delta, L nominal plus 2 delta, right? So delta can be anything, right? You could decide, right? Delta may be 50 or 100 nanometer. Then if so then you take different transistors in the same technology, different gate length, then find the I on and I off and plot it, and it will always be a straight line. That is called the universal curve of that transistor. Okay. So also one class before we talked about scaling, right? And we also briefly, because we didn't have enough time to discuss about scaling, but I told you, right, because we are continuously scaling the transistor dimensions. So when I talk about scaling the transistor dimension, that means scaling L, width, and pitch, and all this dimension of the transistors proportionately, right? So we have moved from 10 micrometer technology, which is the starting technology of the CMOS technology in 1970s, to all the way we are talking about 5 nanometer CMOS technology now, and in future maybe we'll go to 3 nanometer CMOS technology, right? So here, if I take two examples of 250 nanometer and 7 nanometer, right? Let's say this is around 22 years of gap, 22 to 23 years of gap between these two technologies, right? So if you see, means this is just a graph, because so if I plot this 250 nanometer, so universal curve of 250 nanometer CMOS technology and universal curve of 7 nanometer CMOS technology. So what has been done is your universal curve, when you are scaling the transistor, right? So when you are developing a new technology, right? So the goal is to move the universal curve to the right, right? So universal curve should always move right? So if this is 250 nanometer, then the 7 nanometer should be to the right of the 250 nanometer, right? So similarly, 180 nanometer is to the right of 250 nanometer, 130 nanometer right of 180 nanometer. Similarly, we move from 250 nanometer to 7 nanometer, right? So the purpose of scaling is to shift the universal curve, right? So when let's say TSMC is developing new technology, so it will always compare its new technology with the old technology. Let's say 3 nanometer technology with 5 nanometer technology, right? And 3 nanometer technology universal curve should be at the right of the 5 nanometer CMOS technology curve, right? If it is in top of each other, or 3 nanometer is the left side of 5 nanometer, then nobody will buy that technology, because 5 nanometer is not better, right? Then see, if 3 nanometer is towards the left of 5 nanometer technology, let's say here, right? So when I'm talking about when I'm comparing 250 nanometer and 7 nanometer, here you see at the same off current, your 7 nanometer gives more on current, right? Which is desirable, right? But तुम्हारा 7 nanometer curve इस side होता तो, right? So let's say 7 nanometer curve is the right hand side. Then at the same off current, your 7 nanometer will give you less on current, right? But nobody will be interested in that, right? Because I want, when I'm talking about advancement of technology, I want my on current should improve at the same off current, or off current should decrease at the same on current, right? So yeah, so you see here, I mean, between 250 and 7 nanometer, at the same off current, on current has increased almost 5 times, right? On current has increased almost 5 times in the last 22 years, right? So when we're talking about on current, so you see, we are currently talking about on current from a single transistor, right? We are talking about around 1.5 microamperes per micrometer of current, right? 1 micrometer width, right? We have 1.5 milliamperes of current, right? So that is that is the current technologies, right? 5 nanometers, 7 nanometer, right? In early time, into 20 years back, we are only talking about 250 to 300 microamperes per micrometer, right? From the technology, right? Even if you look at 180 nanometer CMOS technology, so you are hardly talking about 400 nanometer, 400 microamperes of micrometer current, right? So current driving capability of the transistors has increased. That means the transistors are becoming faster and faster, right? Okay. Similarly, if you talk about off current, right? Let's say I do not want on current, right? So when the advantage of scaling is at the same on current, right? Let's say my on current is fixed. My on current is fixed at 1 milliamperes of micrometer current, right? Right. So at the same on current, if you compare this 250 and 7 nanometer CMOS technology, the off current has reduced by 5 orders of magnitude, right? With time, means this is in last 20 years. If you only look at the off current, at the same on current, your off current has reduced by 5 orders of magnitude, right? So this is the advantage. This is what the scaling has done for us. This is how the semiconductor industry has evolved over the years, right? So here I have taken a slide from Intel. This is quite old slide. That means around 5 to 6 years back slide. But this gives you the information, right? So they have plotted the universal curve of their different technology generations, right? They have started with 65 nanometer. Please understand this. So this is 65. So they have plotted the universal curve for 65, 45, 32, 22, and 14, right? So 5 different CMOS technologies they have plotted, right? So here you see, so as I told you, right, universal curve for every new technology has to shift to the right. That is the advantage, right? Otherwise, nobody will buy the new technology, right? So here, if you see, right, so if I at the same off current, right, at the same off current, my on current has improved. Technology is technology, right? At the same off current, let's say I'll take, okay, my power. So when I'm talking about desktop, right? When I'm talking about laptop, let's say your laptop is a 30 watt laptop or your desktop is a 65 watt desktop. That means your power is fixed, right? So power is fixed. That means your off current is fixed. So, but at the same power, I am getting higher performance, right? Right? That is what the scaling. That means if you have your microprocessor in 65 nanometer node or in 14 nanometer CMOS node, even if your power is fixed, let's say your desktop, your power is fixed at 65 watt, but you are getting 5 times advantage in the speed, right? So this is the means effect of scaling. Right? Or if I'm talking about from off current point of view, if let's say I'll fix my speed same, right? Let's say I'll be, okay, my processor will be only 1.6 gigahertz processor, right? Right. If I keep my speed fixed, if you see my off current between 65 and 14 has reduced by almost 1,000 times, right? Right. So there is a 1000x reduction in off current. That means if I am talking about 65 watt processor, right, in 65 nanometer node, when I go to 14 nanometer node, this will be 65 watt by 10 to the 5. This will consume very less power, right? But so when it consumes very less power, I could increase the number of transistors, right? I could increase, so I could increase the number of transistors, still keep the same power, right? Right. So, so this is one of the advantages. This is how the semiconductor industry has improved over the years, has advanced over the years. And because I always talk, means I always tell my students or wherever I give talks, right? So when we see the product, right? So we are talking about, all of us have smartphones now, right? Right. But when we are students, like in early 2000 or early 2000s, we do not have a phone, right? So we do not have a smartphone. But that doesn't mean that people didn't have idea, right, to have smartphones. But technology was not available to have a smartphone that time. This is because if you look at, see, in before 20 years, when I'm talking about, right? So before 20 years, right? Your off current was 10 to the 5 times higher, right? So when your off current was 10 to the 5 times higher, you cannot have a portable computer with you, right? So your smartphone is a portable computer, right? You cannot have a portable computer, right? So, so the point here is, what I'm bringing here is, so the product, right? When we're talking about products, right? When we're talking about very good products, right? Like very low power, high speed product, right? So that totally depends on technology, right? So smartphone is available now because technology made it available, right? If you do not have proper technologies, you will not have smartphones now also, right? If the industry has not scaled, right? If the industry would not have scaled, right, in the last 20 years, they have not continuously reduced the off current at the same on current, or increased the on current at the same off current, then you would not have seen, right? You would not have seen a smartphone now, right? On coming back to Intel, so they this is just the product, right? So for when they're talking about smartphone processor for a smartphone, so they don't worry about the speed, right? So where there is the power, so this smartphone is always at the low end, right? So that means uh, you keep the performance same, right? You keep the performance same, but you reduce the power continuously, right? So that your battery capacity, right? Okay, you could charge, means if you bring a new smartphone, it is telling you, okay, now you could charge for 12 hours, means you could have your smartphone without charging for 12 hours. Somebody claims, okay, you could have your smartphone without charging for 24 hours. This is they're telling because they could be able to, means they could design a circuit which is a low power circuit, right? It's not consuming lots of power, right? And that is possible because we have technologies available which has very low leakage, low power technologies, right? All right. So this is about scaling. But now let's move ahead. All right. So we talked about threshold voltage, right? Threshold voltage is a major parameter of your transistor, right? All the performance, right? On current, off current depends on threshold voltage, right? And threshold, when you design a transistor, the first goal is to set the threshold voltage at a particular point, right? So that is the first thing, right? Because threshold voltage is very important. It will change your on current and off current, right? So, but the threshold voltage, if you look at the equation of the threshold voltage, your threshold voltage VTH is nothing but flat band voltage plus 2 psi B plus this equation we know, right? We have so this is nothing but QD by Cox, right? Depletion charge by Cox, right? Okay. So out of this, right? Out of this, let's say 1, 2, 3, 3 three parts of this equation, VTH. All of these are temperature dependent, right? So if you look at the flat band voltage is also temperature dependent. Psi B, your psi B is KT by Q ln Na by Ni, right? This is temperature dependent because here there is a temperature term here, and Ni is also depends on temperature, right? Flat band voltage has your band gap coming into picture, right? And this is temperature dependent, right? So your threshold voltage depends on temperature, right? So let's see how does it, means what is the sensitivity, means basically we want to know what is dVTH by dt, right? If the temperature increases by a certain amount, how much the threshold voltage increase or decrease, right? Okay. So if you see your flat band voltage is work function of gate minus work function of your semiconductor, assuming that there is no charges, right? Because even if there are charges, even if for oxide there are some charges, but these charges do not change with temperature, right? So let's say your flat band voltage is phi m minus phi s, which is phi g minus phi s, work function of gate minus work function of semiconductor. So this is taking an NMOS transistor into account. Let's say we'll take NMOS transistor. So your gate is N plus poly. So your work function is the electron affinity, right? Your work function is electron affinity, and the work function of your semiconductor, this is p type. This is nothing but electron affinity plus half a band gap plus your psi b, right? And if you look at the flatband voltage is Eg minus Eg minus by 2Q minus Ib, and we know, right, this is around 0.9 volt, right? Okay, minus 0.9 volt. So here this is flatband voltage. Then if I look at if I plot this flatband voltage here, right? So this will be minus Eg by 2Q minus Ib plus 2 Ib. This will be plus Ib, right? And this factor, right? Root over 4 epsilon psi Qna root over by Cox into root over psi. This is your flatband. I mean, this is your threshold voltage, right? Okay. So here also you could see means your since your threshold voltage depends on band gap, right? So if you change the band gap, your threshold voltage will change because both your psi b will change, your Eg will change, right? So if you go to a material less than silicon, right, a band gap less than silicon, right, then your threshold voltage will decrease because your Eg has reduced as well as your psi b also will reduce, right? Okay, so this is your threshold voltage equation. Then if I do VTH, so then I have to take the dVTH by dt, right, just to see how does it change the temperature. So this is your threshold voltage, right? If we take the derivative of that with respect to temperature, so this will be first term will be 1 by 2q dEg by dt. This is d psi b by dt because psi b is also temperature dependent. So this part is a constant. This is fine. So, but this part will be temperature dependent, right? So d by dt root over psi b. Then if I do some math, right? So I could still write it as so d by dt root over psi b. I could write 1 by 2 root over psi b into d psi b by dt, right? If I collect all the things, so my dVTH by dt will be in this form, right? So first term will be 1 by 2q dEg by dt plus d psi b by dt multiplication this factor, right? So if you look at this factor here, right? So this is nothing but your get control, right? So right. So because if you look at your depletion capacitance, so I have written here M, right? So because we are talking about when your Vg, because when you're talking about threshold voltage, that means your psi s is equal to 2 psi b, right? So when psi s equal to 2 psi b, so your depletion width has become maximum. After that, after psi s, because after that, your means if you increase the Vg beyond this voltage, your surface potential does not change much, right? Your stays same at 2 psi b, right? So that's why this CD, because CD is epsilon Si by WD. Since WD is maximum, your depletion width is maximum. That maximum will happen when psi s becomes 2 psi b. So your depletion capacitance becomes minimum, right? So we have seen in CV curve, right? Your depletion capacitance decreases till inversion, then it suddenly increases again, right? Right. So the minimum depletion capacitance is nothing but epsilon Si by maximum WDM, means maximum depletion width. And I know this math, right? So I could put the equation for W means depletion width. Then I'll see that, okay, so your this factor here, root over epsilon SiQNA by Psi b is 2 CDM. That means this is 2 CDM. So this if this is 2 CDM, then I could I could put this 1 plus 2 CDM by Cox here, right? So 1 plus 2 CDM by Cox. And I know that your M factor is nothing but 1 plus CD by Cox. So this will be 2M minus 1, right? So your dVTH by dt is nothing but 1 minus 1 by 2q dEg by dt plus d psi b by dt into 2M minus 1, right? So now I have to see how your band gap changes with temperature, how your psi b changes with temperature. For that, I have to again look at psi b. Psi b is kT by q ln Na by Ni. That means I could write in this term kT by q ln Na minus kT by q ln Ni. If you do the d psi b by dt, right? So this term will be k by q ln Na. T will be gone, and again this will be k by q ln Ni plus Kt by Q d by dt ln Ni, right? Right? This is simple mathematics, right? We know our Ni is root over NCNB e to the power minus Eg by 2 Kt. So I could write ln Ni like this, and if I yeah, so another thing is, you know that NC and NB are proportional to T to the power 3 by 2. So I could write this root over NC and NB in this form. C times T to the power, C is a constant, T to the power 3 by 2. So ln root over NC and NB will be ln C plus 3 by 2 ln T. So because I have to connect, because I have to make the thing simpler, right? So then going here, so ln Ni is ln root over NCNB minus Eg by 2 Kt. Then I could write down this, right? Right, ln Ni is this much, right? So here I have a in this here I have a d by dt ln Ni term. So if I do d by dt ln Ni, so this ln C will be gone. So this will be 3 by 2t, because ln T, derivative of ln T is 1 by T, and this has Eg by 2 Kt square minus 1 by 2 Kt dEg by dt, right? So so this is simple mathematics again, and because I have a Kt by Q multiplied here, Kt by Q d by dt ln Ni, so I could also find it out, right? What is Kt by Q d by dt ln Ni will be in this form, right? Right. So again, I mean, basically what I'm doing is I'm just simplifying these equations. So I'll have d psi means you could look at this derivation, because I'll share the video anyway. You'll look at this derivation. So d psi b by dt will be in this form, right? Then again, your dVth by dt, right? Your dVth by dt is nothing but 1 minus 1 by 2 q dEg by dt plus d psi v by dt 2m minus 1, which we have written here, right? This one. Then if you simplify everything, right, your dVth by dt will be in this form, right? So if you look at here, so your dVth by dt is nothing but m minus 1 by q. M is the 1 plus Ct by Cx. This is a gate control factor, right? M minus 1 by q into dEg by dt minus 2m minus 1 k by q. K is the Boltzmann's constant. Ln root over NCNV by Na plus 3 by 2. Right? So this is your threshold voltage. How the threshold voltage? This is the sensitivity of threshold voltage to temperature, right? dVth by dt. Now I could plot, I could put the data, right? So let's say if this is my equation here. So let's say I told you, right, your M is around M is around 1.1 to 1.2. Let's say put M equal to 1.2, right? And dEg by dt we know, because this for silicon, you know, right? For silicon the value is nothing but around 2.7 means basically 0.27 millivolt per Kelvin, right? So for Kelvin change in temperature, your Eg changes by around 2.7 milli electron volt, right? Sorry, 0.27 milli electron volt, right? So this part we know for silicon. Again, this is for silicon, right? So this is for silicon. So for different semiconductor, this will be different. You could find it out from the data sheet. This is your Boltzmann constant, and we know NCNB for silicon. We could put it, right? Let's think. Okay, if Na equal to 10 to 17, if Na equal to 10 to 17, if you calculate, you will see that dVth by dt is nothing but 1 millivolt per Kelvin, right? Minus, right? So what does this tell you? So your threshold voltage reduces with temperature, because I have a minus term here. If you increase the temperature, my threshold voltage reduces, right? And that sensitivity is nothing but 1 millivolt per degree Kelvin, right? But please keep in mind this 1 millivolt per degree Kelvin for the assumptions that I have taken. I have taken M equal to 1.2, maybe M equal to 1.1 or 1.3 depending on your transistor, and I have taken here Na equal to 10 to 17, right? But if your M and Na change, then your dVth by dt will also change, right? Okay. So here what I'm telling is dVTH by dt for the things that have taken is minus 1 millivolt per degree Kelvin, right? So for a Kelvin change in temperature, my threshold voltage will change, reduced by 1 millivolt, right? So typically, so if you see, when you're operating a integrated circuit, right? So your temperature increases. Means, see, we always qualify our ICs from minus 65 degrees Celsius or to 105 or 125 degrees Celsius for processors, right? So that means, so there is a possibility that temperature increases by almost 100 degrees Celsius, right? Because as I told in the last class, right? So as you're operating a microprocessor, your power is continuously dissipated, right? That means this power is converted to heat, right? That means it heats your integrated circuit, right? So if your thermal management, means you also remove this heat, right? You have coolants and all those things to remove this heat, right? Passive cooling or active cooling. But the point is, but still, even if you see, basically your cooling system will manage the temperature, right? It will not allow the temperature to increase exponentially, right? It will just manage the temperature, right? But there is a, so that manages temperature means it will not allow the temperature to go beyond 100 degrees Celsius or so, right? This is the specification of your cooling, right? So even if your temperature changes by 100 degrees Celsius, that means your threshold voltage will change by minus 100 millivolt, right? Right. So during the operation of the microprocessor, means, see, your IC, your threshold voltage is changing by 100 millivolt, right? What is the significance of VTH changing by 100 millivolt? Because 100 millivolt, you see, what is your subthreshold swing, right? Let's say your subthreshold swing is 60 millivolt per decade. Let's say you have designed a very good transistor where the subthreshold swing is let's say your subthreshold swing is 100 millivolt per decade, right? 100 millivolt decade is not a very good subthreshold swing, right? That means if your threshold voltage changes by 100 millivolt, your off current will change by decade, right? Or off current will change by 10x, right? So basically your threshold voltage reduces, that's fine. Your threshold voltage reduces is fine, but threshold voltage reduction has a significant impact on IOF. IOF will increase by 10x in this case, right? Right, because your subthreshold swing is 100 millivolt per decade, so it will change by 10x, right? So, and you see, this is the 10x increase in a single transistor, right? In your microprocessor, you have 1 billion, let's say 1 billion transistor, and you could imagine how much current, means how much off current and off state leakage will increase, right? So, see, this is another disadvantage of of heating, right? Because we want to manage heating. That's the reason we want to talk, means our coolants, means basically we need to cool, we need to remove the heat from the processor as soon as possible, right? Because the moment your IC is heated, your off current will increase, and if your off current is increased, IC will be heated more, right? So this is again a positive feedback, right? So basically, if you don't want your IC to fail, right? So basically you want your dVTH by dt to be low, right? But this is not possible, right? So because this is a fundamental parameter, this means definitely this will depend on M and Na, but the M and Na that we had chosen, they are not very far from the, means what we are using in the transistor, right? So you will typically get 1 millivolt per degree Kelvin change. That means your threshold voltage is changing and your off current will change drastically, right? So that's the reason. Okay, that's the reason you have to know about this, right? That's the reason when you design your microprocessor, you also see the performance of your microprocessor at different corners, right? Because you have to meet power spec, right? You have to meet power spec in at different temperatures. So you simulate your designed IC at different temperature and see whether you are still in the power envelope or you have overseeded it, right? Or you are exceeded it. Okay, so this is about VTH. VTH means this is about change in threshold voltage with temperature. But with temperature, we have already discussed earlier, with temperature, your mobility, the electron hole mobility also changes, right? And how does it change? Because once your IC become high, if your silicon is heated, right? If your silicon is heated, so your phonon scattering, so mobility will depend on three scattering, right? One is ionized impurity scattering or phonon scattering, right? Right. So your phonon scattering, because your vibration will increase, right? So once the silicon is heated, that means your mobility also reduces, right? With temperature, your mobility also reduces, and the mobility also reduces. That means it will affect your on current, right? Mu Cox double by L, VDD minus VTH square, right? Right. So with temperature, your VTH reduces, right? This is a good thing. Your on current will increase, but your mobility reduces with temperature, right? And the mobility reduction is too much, right? So here, let's say if your VTH reduces by, let's say your VDD is 1.8 volt, and your VTH was let's say 0.8 volt. That means you are talking about this factor is 1.8 minus 0.8 square, which is 1, right? But if your VTH reduces by 100 millivolt with 100 degrees Celsius change in temperature, so this will become 1.8 minus 0.7 square. This will become 1.21, right? So 1.21, that means your on current is increases by 20%, right? Because 100 millivolt change in threshold voltage, your on current increases by 20%, but your mobility will degrade significantly, right? So mobility actually degrades more than 20%, right? So overall, your on current also reduces with temperature, right? So means I don't know how many of you have done this, because you could have easily done, because this I had planned to have characterization in this course, microelectronics lab, but we could not do this time because of this COVID situation and restricted access to the lab. But if you measure your MOS transistor at different temperatures, right? If you just, I'll show you a simple IDVG, right? So if I take a simple IDVG, right? IDVG, your transfer characteristic, right? So let's plot in the linear. So linear, your something like this, right? Your IDV means your transfer characteristic does look like this, right? Let's say this is a temperature of room temperature, 27 degrees Celsius or 300 degrees Kelvin, right? But if your temperature increases to 400 Kelvin, right? So your threshold voltage will reduce by 100 millivolt, right? This is a threshold voltage reduction by 100 millivolt, and your mobility will also reduce, right? So basically, you will have a curve like this, right? So this is for temperature equal to 400 Kelvin, right? So here your threshold voltage reduces, and your on current also reduces, right? Because right. So because of the mobility degradation, right? So that's the reason. That's the reason. Means you are losing with temperature. You are losing in both ion and IF, and your ion by IF ratio is severely affected because of temperature change, right? And okay, right. And this ion by IF. This is nothing but your switching, right? Switching performance, right? Right. And switching performance is overly affected. So that's the reason. If you want to really have very high speed and low power circuits, you have to operate that at low temperature, right? If you go to low temperature, means you could go to, let's say, 77 degree Kelvin. That means you are going 200 Kelvin below, right? Right. So your threshold voltage will increase. Your mobility will also improve, right? So basically, you will have a better transistor, right? Can have a better transistor, right? Means I could not draw it properly, but it could have a better transistor, right? Right. So let's say this is T equal to 100 degree Kelvin, right? So at low temperature, actually your transistor will perform very well, right? So because your VT has increased, that means your off current has reduced, right? And your on current has improved because your mobility has reduced. So IM by I, overall IM by IF ratio will go, means will increase, right? So so that is means so many cases, right, for very high performance circuits. So means I mean, you operate your ICs at very low temperature, right? If you want to get speed and power both from your integrated circuit. All right. So any questions here? No
Sir,
questions? Yes.
sir, when we were starting, you draw the ion versus ion graph. So there, when we were talking about L nominal, so when we,
L nominal will be defined in your design manual, right? Huh?
sir, in you while going up the curve, you added plus minus delta, and going below plus delta. Sir, uh,
Because if you reduce
how
the length, okay, we have not yet done this. Means basically, your threshold voltage changes with length of the transistor, right? And we will discuss that, right? When we do the short channel effects, maybe today, may not be today. Tomorrow, maybe we'll discuss. So basically, see, or you think in this way, right? Your on current, right? Mu Cx W by L, VDD minus VTS square, right? So if your L is reduced, right, that means your on current will increase, right? Because your on current will increase, so you'll move. Means you will go with reduction in L, you will move in this direction, right? With reduction in L, also we have not yet discussed. Reduction in L, your threshold voltage also changes. Your threshold voltage actually reduces, right? So the moment your threshold voltage reduces with reduction in L, so you'll see a change in off current, right? Right. That's the reason both on current will increase and off current will increase when you reduce L. That means your curve, means your transistor will go off, right? Clear,
yes,
Om?
yes, yes.
Okay. Any other questions from anybody? All right. So if not, so then let's move to um, our next topic. Uh, so now we'll talk about in the next two classes that we have, and whatever remaining time we have today. So we'll talk about the second order effects in MOS transistor. Um, right. And when I talk about second order effects, we have channel length modulation. So this is the first thing, right? Channel length modulation. Then we'll also talk about velocity saturation, right? Um, Velocity saturation. We'll talk about charge sharing, because this is the effect which is the major means this affects your threshold voltage. I was telling, right? Your threshold voltage reduces with reduction in L. This is because of charge sharing. Uh, Also, we'll talk about drain induced barrier lowering, right? Drain induced barrier lowering. This is a major second order effect in advanced transistor, means basically in very short transistor. And we'll also talk about drain source resistance, right? Drain and source resistance. Let's say if you could discuss all of them, then it will be really nice ending to our course, right? All right. So let's start with channel length modulation. I mean, so all of you know, right? What is mostly if you have done analog circuits course, so we have there is a discussion about channel length modulation. Uh, Basically, the channel length modulation is, let's say you are operating a transistor in saturation. So when you're operating a transistor in saturation, so let me draw, right? When you're operating a transistor in saturation, so your channel has been pinched off, right? So I mean, this we discussed, this is your inversion layer, right? And your channel has been pinched off, right? So this voltage at this point is always VGS minus VTH, right? This part we know, right? This is VGS minus VTH, right? Right? And this is the pinched off, right? And let's say the total length of the transistor is L, right? And if this is so this is the delta L, right? So actual inversion channel inversion layer length is L minus delta L, right? So delta L is the pinched off portion of the channel, right? So what you're telling, right? So when the transistor starts to pinch off, right, that means your delta L is 0, right? When your transistor start to pinch off, that means delta L is 0, right? Then, and that happens when VDS equal to VGS minus VTH, right? Right? Right. So now, if you go beyond VGS minus VTH, if you increase VDS more than VGS minus VTH, right? And I told you this point here will move towards source. That means your delta L will increase. That means your delta L will increase, right? So, if because when I'm talking about saturation, the current equation that we have derived is mu Cox W by L VGS minus VTH whole square, right? And this L is the length of the transistor. And during that discussion, we have assumed that this L is higher than delta L, right? Because pinched up portion is always there, but our length is very high. Length is long. We have a long transistor, so L is greater than delta L. But this may not be true, because when you're scaling the transistor, dimension, my L is reducing, but my delta L is not reducing, right? Because the moment your VDS will go beyond VGS minus VTS, your delta L will increase, right? So in that case, this ID will be mu Cox, because we could only write mu Cox W by L effective, because this is the effective gate length, which is L minus delta L times VGS minus VTH square, right? This will be your ID, right? And if I have this L effective is nothing but L minus delta L, right? L effective is nothing but L minus delta L. So here, what is the thing? That as your VDS is increasing, right? Because your VDS, if you will go on increasing, so because we started this equation, your ID is independent of VDS, right? ID is independent of drain to source voltage. So this behaves like an ideal current source. That means your ID is flat, right? So this doesn't change with VDS, right? If you plot ID and VDS, your ID is not changing. The moment the transistor saturates, your ID is not changing. But this is not true. This is only true for long channel transistor, right? When L is much higher than delta L, right? If the L is not higher than delta L, if L minus delta L is some portion of L, that means you cannot neglect delta L. In that case, you see, as your VDS is increasing, your L minus delta L is reducing. That means your denominator L effective is reducing. Your ID will increase, right? So ID will slowly increase. So you have a finite slope, right? And this finite slope, this phenomena is called the channel length modulation. This is exactly same as the base width modulation that we discussed in bipolar junction transistor, right? In bipolar junction transistor, we also told, right, if your base width is very small, if you go on increasing the reverse bias across the base collector junction, your base width will continuously, neutral base width will reduce. That will increase your IC as a function of VCB, right? Similarly, here VCE, but here here your ID VDS will not be flat. ID will have a finite slope, and that slope will be nothing. Let me write down. So your ID is mu Cox W 2L effective VGS minus VTS square, and the slope is nothing but del ID by del VDS, right? Right. So so if you take, right, so if you take the derivative, then basically you could mu Cox W times VGS minus VTS square divided by 2, then I'll have del by del VDS 1 by L effective, right? Right. So because L effective is VDS dependent now, right? L effective is L minus delta L, which is VDS dependent. So if I take this del by del VDS 1 by L minus delta L, right? And I could write down this as del delta L times right. I could also write down. So basically I'm trying to have a mathematical equation. This is 1 minus L minus del whole square, right? And this will be minus delta L by del VDS, right. So basically your del ID by del VDS, I could write down, right? So if I do that, so this will be mu Cox W VGS minus VTS square divided by 2 times L minus L effective square. So this is L effective square, right? Times del L by del VDS, right? So this is nothing but our ID sat, means ID sat divided by L effective, right? And this is delta L by delta VDS, right? Okay. So this so basically let me write down it properly. So del ID by del VDS is nothing but ID sat by L effective del, right? So so this is nothing but your lambda times ID sat, we always tell, right? Because lambda, this is lambda is nothing but, you could write your lambda is nothing but 1 by L effective uh, delta L by del VDS, right? So this is the lambda, we call it the channel length modulation factor, right? Channel length modulation factor lambda. So this just tells you how much, means this lambda uh, means basically this just tells you the slope, right? Because your ID sat has a finite slope now. So this just tells you, lambda just tells you the slope, right? So here, if you look at this parameter here, right? If you look at this factor here, right? So your lambda depends on this del, means how your delta L changes with VDS, and since delta L change with VDS depends on doping, right? It will depend. It will be a function of doping. If your doping, if your substrate doping is high, then the change in delta L with VDS will be low, right? So your lambda factor will depend on L effective, as well as it will depend also on doping. And typically your lambda varies from 0.1 volt inverse 1 by volt to 0.001, right? So basically, typically, right? So if you, I mean, transistors, you could also measure what is your lambda, and 1 by lambda we call it your only voltage. Your only voltage 1 by lambda is mostly so basically your only voltage of your transistors varies from 10 volt to 1000 volt, right? So 1000 volt, that means it's a very good transistor, right? Because your channeling modulation is very less. That means your is a very good transistor, and 10 volt is okay transistor, right? So 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 your 1 by lambda is mostly termed as your only voltage, like your base width modulation also we have defined your only voltage, right? uh, so your, if you want to measure the only voltage of a transistor, so if you have a finite slope here, right? If you have finite slope here, if you extend it and wherever it crosses the x-axis, this is your only voltage, right? Right. So please keep in mind your only voltage, of your transistor will depend on Na, right? Your substrate doping, right? Higher the substrate doping, higher will be the only voltage, right? But you cannot really go on increasing your substrate doping, because your substrate doping will also increase your threshold voltage, right? So basically we do not want our threshold voltage to be very high, because it should be less than VDD anyway. Plus, because your on current is proportional to VDD minus VTH square, right? So you cannot have very high threshold voltage. If you have very high threshold voltage, your VDD minus VTH will reduce, then your on current will reduce, right? So you keep your threshold voltage around 0.3, 0.4 volt, right? That's the reason your NA is also fixed, right? So your only voltage. So see, there is a trade-off, right? If you want to increase only voltage, which is better, because if you want a very good transistor, which will have less channel length modulation, you want to have higher NA, but higher NA will increase threshold voltage and reduce ion. So you have to achieve a trade-off, right? So you just find a trade-off. Okay, I want my only voltage to be around this time, right? Around this voltage, without affecting your threshold voltage much. So this is the channel length modulation, and channel length modulation is a very important in very small transistors, right? So when I talk about very small transistor, let's say I am talking about 7 nanometer CMOS technology, right? 7 nanometer CMOS technology. So your gate length in this technology is around, your gate length is around 12 to 14 nanometers, right? So this is very small, low gate length, right? So 12 to 14 nanometer gate length, right? And when you talk about delta L, right? Delta L might be few nanometers, right? So your only voltage will be very low. Only voltage actually is very low in these transistors, right? So if you take one of these transistors and measure, you will see that it will have characteristic like this, right? So this slope, one reason behind this slope, IDVT slope, is your only voltage, your channel length modulation, right? Another factor we'll discuss the charge sharing and debug. But so this finite slope in your output characteristic, one factor is your channel length modulation, right? The one factor is your only voltage and channel length modulation. Okay, so I think it's already 12. Let me stop here today.